Hi everyone, my name is Angelica and I'm glad for having this opportunity to present our team to you. We are the Mobile Robotics Laboratory from the Institute of Mathematics and Computer Science at the University of São Paulo. We conduct research in several areas related to mobile robotics and intelligent transportation systems. Since 2010, our lab has been focusing on researching about self-driving vehicles, which made us the pioneer of Latin America in navigating on public urban streets with a self-driving car, and also in developing the first autonomous truck. I'm talking about the CARLA project and the smart truck. Our team is constantly working on improving the key points of a self-driving vehicle, namely trajectory planning, scene perception and understanding, navigation control, fault detection on the autonomous systems, and even negotiation between vehicles for safe driving. We saw the CARLA challenge as an opportunity, and I will tell why. Our big motivation has always been to help the community with safety and efficiency in traffic. We believe that advanced autonomous systems have the capacity of providing those values. But, as everyone may know, developing a self-driving car isn't an easy task, and it's difficult to compare with other works when each of them has its own metrics. The CARLA Challenge, however, will be providing a way to benchmark autonomous systems developed by several teams around the world. We are confident about our work, but we also know that there are many talented participants in this competition.
The idea behind our strategy on this challenge was to create a common architecture for all tracks. Of course, each track has a different set of sensors, which is a very challenging aspect on this competition. But talking about just the design of architecture, it is possible to create a common design and change the implementation of few components, keeping the communication interface. And it is what we did. So our architecture has 4 layers. We choose ROS for framework because we already use it in CARLA. And the first layer is called Agent, which is similar to sensor layer for autonomous vehicle, and it also communicates with the CARLA. Then we have the perception layer, which is responsible for traffic sign, traffic line detection and classification, and for obstacle detection. Finally, for navigation, we have the decision-making and path planning layer, finished with the lateral and longitudinal controllers in the controller layer.
For the perception task, we use cameras and LiDAR sensors. We use point clouds coming from LiDAR scans and stereo vision ELAS algorithm. Obstacle detection is performed by both static and on-road obstacles. We model their behaviors and movements. Finally, synthetic images provided by CARLA simulator were collected for training, validation, and testing for this system.
Our decision-making framework is built on Markov decision process, which is a powerful tool to model systems in which uncertainty cannot be neglected. In the challenge, uncertainty mainly arises from traffic light states and the behavior of other traffic participants. In order to simplify our model, we only consider longitudinal actions, follow a reference speed, accelerate or decrease speed. The decision-making model generates a reference speed that is passed to the low-level control, which is responsible to generate throttle and brake commands. To do so, we use a proportional integral control. For the lateral control, our agent uses a non-linear predictive module control. Constraints are added in order to respect the kinematic limits of the vehicle. The performance of our controller is mainly verified at sharp corners, where collisions with guardrails and sidewalk invasion are avoided, and also at high speeds, where the vehicle stays at the global route with low lateral deviation.
We are here to seek the first place, and not less important, to learn with the others.